You ever wonder how a tiny little blueprint can turn into a massive, towering skyscraper? Well, the secret is all about geometry, specifically something called similar polygons. And today, we're going to crack that code.
So let's start with a little puzzle. I mean, a blueprint and a skyscraper. They're obviously way different sizes, right? But they're connected. There's this really special mathematical link between them. Any guesses what that is?
You got it. They share the same shape, just not the same size. And that, right there, is the heart of similarity. And once you start looking for it, you'll see this concept is all around us. Think about it. From toy cars to architectural models, it's all governed by a pretty simple but powerful set of rules.
Okay, Section 1, the rules of similarity. So what officially makes two shapes similar? Let's dive into this and get to the bottom of it.
Right, so in geometry, it's not enough for two shapes to just kind of look alike. Nope, the word similar has a very, very precise meaning, and it all boils down to two conditions that have to be met.
Now, what's really cool about this image is it shows those two critical conditions visually. First, check out the angles. They're preserved. They stay the same. But the side lengths, they get scaled proportionally. It's like you're using a photocopier to enlarge or shrink it. The shape stays the same, just the size changes.
And this is the absolute crucial point. You have to pass both of these tests. I mean, both. The corresponding angles have to be equal, and all the corresponding sides have to be proportional. That constant ratio of the sides, that's the secret code we're talking about. We call it the scale factor.
All right, Section 2, finding a missing side. Let's actually use this code now. See, once we know the scale factor, we can use it to find all sorts of missing information.
Okay, here is a classic problem. We've got two triangles, and the good news is we're told they're similar. But one side is a total mystery. Our mission is to find the length of side X.
So the first step is always to set up a proportion. And don't let that word scare you. A proportion is just a statement that two ratios are equal. We just have to match up the corresponding sides. So the side MN on the big triangle matches up with DE on the little one. Simple as that.
Okay, now we just plug in the numbers we know right from the diagram. So 18 over 15 is going to be equal to 30 over, well, our mystery side, X. And now for a little bit of algebra magic. We do what's called cross multiplication. We get 18x equals 450, do a quick division, and bam, x equals 25. See, this really shows you just how powerful these proportions can be.
Okay, Section 3, scaling perimeters and areas. Now, the scale factor's power doesn't just stop at side lengths. Oh no, let's see how this whole thing builds when we start talking about perimeter and area.
So for perimeters, the rule is really simple and direct. The ratio of the perimeters is exactly the same as the scale factor. It's a one-to-one relationship.
But for area, there's a twist. You have to square the scale factor to find the area ratio. Think about it. Area is measured in square units, right? So the ratio gets squared too. It's k squared.
Let's just put these side by side for a second, because this is super important. Perimeter ratio is k. Area ratio is k squared. This difference is probably the most common trap people fall into. So just remember, area gets squared.
Okay, let's make this real. Imagine a town is building a new pool, and they want it to be similar to an Olympic one. So the Olympic pool is 50 meters long. The new one, 40 meters. So what's our scale factor? It's 40 over 50, which simplifies down to 4 over 5.
And check this out. The perimeter ratio is 120 over 150, which also simplifies to 4/5. It matches, just like the theorem predicted. Perfect.
Okay, so what does this mean for the area? Well, the area ratio has to be that scale factor squared. So 4/5 squared, which is 16 over 25. This is so important. The new pool doesn't have 4/5 of the area, it has 16/25 of the area. That's a massive difference.
All right, Section 4, the similarity test. Now for the final challenge. How do we prove two shapes are similar when nobody tells us they are? How do we figure it out for ourselves?
This is where we have to become detectives. Because looks can be deceiving, right? We have to check both of those conditions we talked about earlier. We can't just eyeball it.
So let's test these two pentagons. A quick check shows that, yeah, their corresponding sides are all proportional. The scale factor is 2/3. Looks good, right? So, are we done? Is that it?
The answer is no, not even close.
And this is a perfect illustration of why we need both rules. See, even though the sides are proportional, when we try to map one onto the other, the angles just don't line up. They aren't congruent. So these shapes are absolutely not similar.
So, here it is, your final checklist. Number 1, are all the corresponding angles congruent? Number 2, are all the corresponding side lengths proportional? If you can't say a big yes to both of those questions, then they are not similar. No exceptions.
So now that you know the secret of the scale factor, think about it. What other shapes in your world are secret copies of each other? From screen resolutions to pizza slices, similarity is literally everywhere once you know how to look for it.